we're approaching towards the end of the course. So I remind you the structure of what we've seen until now. We started yesterday with a theoretical background for the problem of causal inference, and we've seen the issue of endogeneity and how these tools help us overcome this problem. Then we've seen an overview of different tools that can be divided into two large groups. The first group is the RCTs, and the second group is the quasi-experiments methods. In the quasi-experiments methods, we divided them into two groups, type 1 and type 2. Type 1 based on observables, and we've seen two main tools, which are the propensity score matching and the difference in difference. So the third method that we're going to see now is the panel data estimations. Type 2, we're not going to cover them, instrumental variables and regression discontinuity designs. But we've seen them. We've seen some case studies covering these tools. Okay, so for panel data models, as usual, yes.
Just I have points to what I saw that we discuss only test about the coefficient of variable, but we didn't discuss the test of model specifications. That means Fisher test, S-square test, and the test of, how you say, the test of validity of H.
Sure. I mean, definitely we have a lot of robustness tests that can be done for all the tools. But a common point that we have to highlight for all these types of courses, like any other quantitative course, it's a learning by doing. So what we do here is we give an overview of the methodology, how it can be implemented in Stata, but then for the details and for the technical or the expansions in terms of tests and all this, definitely will not be able to cover everything, because it's just, I mean, it's very intensive. So in general, what we do in these courses, we give the basics that help you understand the methodology, how to do it in Stata, and then for the extensions, for the even for some tests, all this, definitely it will have to be, I mean, a learning by doing process. So, but perhaps what we're going to do today, because in panel data it's important, we're going to see some post-estimation tests in order to see which model is better than the other. This is an example of the post-estimation methods that we'll have. But in general, I mean, a rule that you have to bear in mind in any kind of these courses, if you just focus on what we do in the course and you don't practice on your own research, the course is practically useless. Why? Because you have to follow up on your own work with your own data set, then try to apply the do files that we did in the course on your own work. If you face any problems, either you have to ask your colleagues or search online, and now, I mean, everything is really available on Google. So if you just type even the name of the error that you get in Stata, you will get a lot of suggestions, both on either on Stata Forum or on different websites. So, but it's very important that you practice on your own work after the workshop. Otherwise, you will really forget what we've done, and it will not help you in your research. Okay? And I mean, I'm not talking about this course only, but in general, any hands-on training, we never cover all the themes related to some methodologies, because it's impossible. I mean, we're doing in 2 days what can be done over a whole semester, which is very challenging, I mean. So what I'm going to do in this session, I'm going to cover the panel data models. So I will first start with the structure of panel. Perhaps some of you have already worked with panel data, some didn't. But it's important first to see the different types of data sets that we can have. And as I mentioned yesterday, if we have one individual but greater than one time dimension, so this means that we have time series analysis. And for time series analysis, we have to apply time series techniques. And in general, most of the time series techniques can be applied in Stata. If use might be more user-friendly because it's a drop-down menu. You don't have to program everything. But that's for time series analysis. Then for cross-section analysis, if we just have 1 year, but more than one individual. And in general, it's definitely greater than, as a rule of thumb, it's greater than 30. Then if we have number of years that's greater than 1 and number of individuals that's greater than 1, so we're going to have a panel data analysis. And that's what we're going to have in this session now. But the important condition here is that the number of individuals is greater than the number of years, which is our case, because here in our case, we're going to work with the Egyptian labor market panel survey, where we have 2 rounds for the survey, but thousands of individuals at the individual level dimension. And if we have t greater than 1 and n greater than 1, but t is greater than n, so in this case, we apply the time series cross-section techniques, like panel var and so on. So panel data models, what's their, why they are useful? As Arellano mentioned in his textbook, he said that these types of models attempt to account for correlation between observable variables and unobservable variables. And this is important. Why? Because I remind you that the main problem that we had in the identification is that sometimes it's not possible to control for the unobservables. And this can affect the estimation that we're doing. So this is why we have to take into consideration this. And there is also an important concept associated to this, which is the unobserved heterogeneity. What do I mean by unobserved heterogeneity? And perhaps I can start with this and then get back to this point. So for the unobserved heterogeneity, here we have two dimensions for the data set, the time dimension and the individual dimension. So this means that I can have a heterogeneity that can be attributed to the individuals themselves, and this can be a source of omitted variable bias in my estimation, or at the time level, because I have two dimensions for my data set.
And sometimes about error of measure.
Yes, error of measurement.
Of exogenous variable.
Sure. But here I'm just focusing on the individual and the time. This is one of the extensions of the panel data that we can have an error of measurement. But here, for the timing, we're just focusing on the individual characteristics that we cannot observe, or the time characteristics that we cannot observe. And this is why all this unobserved heterogeneity, especially among individuals, because here we have an individual dimension that is much more important than the time dimension. So if these individual characteristics that are not observed, they have an influence on my variable of interest and are correlated with the explanatory variables. So this means that we're going to have a correlation between my error term and the explanatory variables. And in this case, the condition of strict exogeneity is not satisfied. And this is why our results will be biased. So the main idea of panel data estimation is to control for the unobservable characteristics. Okay? More specifically, the panel data models as well as you've just mentioned, sometimes this unobservable characteristics can be either a source of simultaneity bias, so this reverse causality between which is exactly. So in this case, the independent, there is, both the two variables, the explanatory one and the explained variable are correlated, or a measurement error, because in this case, if I have some unobserved heterogeneity, this can affect the way I'm measuring the effect of my independent variable on the dependent variable, because here it results in the independent variables being correlated with the error term, which is basically, which violates the condition of strict exogeneity, and the unobserved heterogeneity, which results in both the independent variables being correlated with the error term and bias the coefficients as well. So the basic idea here is that if we don't control for the unobserved heterogeneity, this will lead to a violation of the condition of strict exogeneity, because in this case, my independent variables will be correlated to the error term, and my results will be biased. So we have to resolve this through the panel data estimation. And in general, what's the advantage of having a panel data set? As I mentioned, we have two dimensions. We have here dimension or time dimension and individual dimension. So this means that I have a higher number of observations. And if I have a higher number of observations, this means that my results will be more reliable, because the more we have observations, the better, the more we have variability, and the more we have more robust results. So the first advantage of this is that it increases the sample size, the panel data sets. Second, we can study the dynamics of cross-section over time, because I'm not just focusing on what happens at a specific point of time, but I'm following the same individual or the same country or the same firm over time. And then I can understand what's going on over the time span of my data set. And third, we can study also more complicated behavioral models, given the fact that we can have some time invariant variables that are not taken into consideration. As I mentioned, how I'm going to measure the IQ of a person. I can use the IQ index, but at the same time, it's not really accurate, because I cannot really say that the IQ of Dalia, for instance, summarizes all her capabilities. There are some things that are not captured by the IQ. So there are some unobservables in Dalia that should be taken into consideration when I estimate the effect of any variable on her income, for instance. So this is why controlling for the unobservables at the individual level, especially when they are time invariant, is very important in this context. What kind of estimations do we have? So here, on the right, in this graph, as you can see, we have different groups of individuals, but all of them, they have constant slope and constant intercept. So by slope, I mean the slope of the fitted line, which is basically the coefficient, the effect of the independent on the independent, or the correlation coefficient between the two variables, and the intercept, which is here. So all the groups, they have constant slope and constant intercept. And in this case, there is no really any difference at the individual level, because what does the intercept measure? What does the intercept measure in general?
The expectation of the dependent variable if the explanatory variables are equal to 0.
Okay, and in more economic terms, for instance, if we take the example of a consumption function, in this case it will be the minimum level of consumption or the minimum level of income. Exactly, so the minimum level that cannot be compressed. So that's the intercept. And the slope, it measures the effect of one variable on the other. In general, if I have an individual dimension that is important and that's heterogeneous across individuals, so this means that I'm going to have different intercepts for each individual. And that's the basic idea of what we're going to see later in fixed effects. Because in the fixed effects estimation, instead of having one intercept for all individuals, we have an intercept for each individual. But all of them, they have the same slope, which means that the effect of the independent variable on the effect of the independent variable on the dependent variable will be the same for all individuals, but each individual has a different intercept. Because we can have an alternative specification where we have both different slopes and different intercepts, and in the, which is the case of here, on the right up there, we have in this case both slopes that are not the same and intercepts that are not the same. And in this case, I have to run a regression for each individual. So to make it clearer, let's take this general form where we have YIT, and I have IT because we have the individual dimension and the time dimension. We have the intercept, which is alpha. We have XIT beta, which is the vector of explanatory variables. Mu I, which is the unobserved heterogeneity at the individual level. So as if here I'm introducing a dummy variable for each individual, okay? Then lambda t, which is the unobserved heterogeneity at the time level, and nu it, which is the error term, okay? So I goes from 1 to n, and t goes from 1 to t. And in general, I can say that this is exactly what we had in the beginning, because for any equation or any estimable equation, we have the intercept, the independent variables, and an error term. So in this case, I can combine the three of them, which are mu I plus lambda t plus mu it in a single term, which is uit. So the idea here is that my error term, okay, the equation I have is, it includes some dimensions that can bias my results. And this is why I have to take this into consideration when I'm going to estimate my function, in order to avoid biased results. Okay? So that's the general form that we're going to manipulate in the rest of the session. What about the pooled OLS? In general, what does pool mean? A pooled data, what does it mean? Sorry?
We put all the data.
Use the mic, please.
We put all the data in one database.
And then? Yes?
The pooled panel is basically you put all the observations of overtime and individuals together.
And?
So we'll have a exactly.
So I do not identify that I'm following the same individual over time. Exactly. That's the difference between panel and pool. So for the pooled data, I just combine different data sets in different years for different individuals. In theory, it should be a panel. In theory, because I have both the individual dimension and the time dimension. But if I do not declare that I'm following the same individuals over time, for stata, it will be a cross-section estimation, because I'm just pooling all the individuals together. So it will be basically an OLS, but that has a time dimension. So when I'm going to estimate a panel, and we'll see this later, I have to declare that there is a time dimension for the data set. So I'm following Iman over the 3 years I have. Okay? Yes?
But in that case, can we do a similar thing to the propensity score matching to see if these, to give the same basic characteristics for people and match them and build ourselves a panel data?
This is pseudo panel.
No, I don't get your point.
Yani, can we match several individuals that we are not sure they are the same people, but they have the same characteristics, basic characteristics? And
You mean, and we don't have...
the code itself?
Yeah, I mean, in some cases, it can be done, but it's not accurate. Because in general, the idea is to follow the same individuals. So, because nothing guarantees that if I observe some characteristics for these in a year and for the same characteristics for another group the same year, and they are similar, so that they are really matching.
But this is what they do in pseudo panels, right?
Yes, we do it. But if we're talking about real panel,
No.
we cannot do this. Okay, and also for some time we do also what we call, I'm not a specialist of this, but I mean, I personally never worked out with these data sets, but sometimes we do also the retrospective data that, based on actual data, we estimate what happened in the past. Okay?
But it must be the same individual, the same observation.
For panel, yes. So,
What about the surveys? Is it we cannot apply validity?
no, but for most of the surveys, and we're going to see later, we have some individuals that are similar to the two rounds that we have, some individuals that exist in the first round and they don't exist in the second round, and some individuals that exist in the second round and don't exist in the first round.
If you look at the income and expenditure survey, Egyptian survey, we will find it is quite the same people, but some people.
No, and it, to my knowledge, the panel dimension of the hikes is very, it's unreliable and it's very small.
Because some people go out, some people come.
So, to my knowledge, the best panel that we have in the region here is the one of the Egyptian labor market panel survey, the Jordanian one and the Tunisian one, yes. Even for the World Bank Enterprise Survey, the panel dimension of the surveys is very small. So, for instance, in the Egyptian case, over the 3,000 firms that we have, not more than 700 are followed over time.
Does the labor survey covers some characteristics like education, income?
Yeah, everything. We'll see this later. Okay? So for the pooled estimation, sorry, let's assume that we have an OLS estimation of panel data that would look as follows. So we have the dependent variable, IT. We have the intercept, the vector of explanatory variables, xit with its coefficient. And as you can see here, the beta does not have an index. So beta does not have an index. And if beta does not have an index, this means that all the explanatory variables, they have the same effect on my dependent variable. Because we're going to see later that we can have what we call the random coefficient estimation. So I will estimate a coefficient, or the coefficient itself will be changing. Okay? Then theta ti, which is the individual dimension, gamma tit, which is the time dimension, by the individuals, delta t, which is the time dimension only, and the final error term, which is it. So this means that if I estimate this with an OLS, in general OLS is applied on cross-section data, right? So if I apply this, so what I introduced compared to a simple OLS, I introduced individual dummies, or dummies at the individual level, which is TI, okay? I introduced time dummies, and I introduced an interaction between both, okay? But I estimate this using a simple OLS. So in order to get unbiased estimates of my coefficients of interest, which are alpha, beta, theta, gamma, and delta, we must have the initial conditions that we know satisfied. And the initial conditions you're all familiar with, so we must have a linearity, meaning that we must have linearity with respect to the independent variables. Here it's x, and time dimension. We must have exogeneity, and by exogeneity we mean that there is no correlation between the explanatory variables and the error term, and if it's violated, so we cannot say that this variable is exogenous, so we have to resolve for this. And the disturbances, which is epsilon, it, must be independent and IID, so independently and identically distributed. They have the same variance, which is homoscedasticity. They are not related to each other. There is no autocorrelation between the errors. So those are the classical assumptions that we have for OLS. Our independent variables are non-stochastic. There is no exact multicollinearity among the independent variables. So if we introduce, for instance, a dummy variable for a certain category, or categorical variable for a certain variable, we have to remove one of the categories that will be the reference in order to avoid the dummy variable trap, which is the fact that we're going to have a perfect multicollinearity. So if we have time invariant individual effects, if I have time invariant individual effects, so this means that some characteristics that do not change over time. like gender, for instance, as we said yesterday, or like the distance between Cairo and Alexandria. It doesn't change over time. So if I have any individual time invariant characteristic, this will violate the two assumptions that we have here, 2 and 3, which are the exogeneity, because in this case the error term will be correlated to explanatory variables. That's 1. And 2, my errors will not be identically and independently distributed. So in this case, I cannot rely on these estimates because these estimates will be biased, given the fact that 2 important assumptions are violated. And this is why we have to estimate this not using an OLS, but using the panel technique. So we have in general, for the panel estimations, we have several types of panel techniques. We're just going to focus on 2, which are the fixed effects and the random effects, because we have also the several other techniques like the dynamic panel, the pooled mean group estimation, and so on. We had another course at ERF for the panel techniques, because there are really several techniques, but here we're just going to focus on 2 types of models, which are the fixed effects and the random effects. And the basic difference between the 2 models is that, let's assume that we're going to introduce the time invariant individual effects, which are here in this case, the UI. So the effects that change at the individual level. So we have the fixed effects and the random effects, and we're going to see that they are basically the same model, but it depends on how I will write it. Why? Because in the fixed effects model, so if you compare the 3rd and the 4th line, you will see that we have alpha in the 2 lines, we have UI in the 2 lines. Here it's in the beginning, in the other line it's at the end. We have nu I in both. We have beta xi, gamma tit, and delta t. So in terms of mathematical notation, it's the same. But it depends on how we're going to arrange the terms. Because in the fixed effects, I'm going to consider that the sum of ui, which is the individual effect, with the intercept represents my intercept. Which means that the intercept in the fixed effects will be what? Will be changing with individuals. And that's what we basically have in this graph. So if let's forget about these 2 lines, and we'll just focus on the 2 scatter plots here that we have. So if I estimate my model using an OLS, this means that the fitted line that I estimate through OLS will be the dotted one. Does this line represent the reality? In theory, no. Why? Because we can see here that there is an important individual dimension that should be taken into consideration. And if we take this into consideration, we must have, for each group, an intercept. So we're going to have alpha 1 and alpha 2, but they are parallel. And why they are parallel? Because they have the same slope. Exactly. Okay? So that's what basically the fixed effects estimation does. So here, this alpha 1 and alpha 2, what does it in practice represent? It represents the sum of the initial intercept that we have, which is alpha, plus the individual effect, which is ui. And this is why the intercept will be changing for each individual. Okay? So in fixed effects model, ui is either a fixed effect specific to each individual, which now includes theta ti, because that's the individual dimension. So each individual has a different intercept, but all individuals have the same slopes. So this means that, just a second. So this means that all the coefficients estimated for the independent variables will not be changing for each group, because we have just one slope for all of them. Error terms have constant variance and satisfy assumption 2 and 3, because now my new error term is what? What's the new error term? is the new, which is similar to the V, right? We call it new. So this error term now does not suffer from the violation of the assumptions 2 and 3. I remind you that the two assumptions were exogeneity and identically and independently distributed. So if I remove the individual effect from the error term, my new error term, which is new, now, I mean, it's okay. There is no problem inside. So UI, which is the individual effect, can be correlated with other regressors without causing a bias. Why? Because in general, does multicollinearity lead to a bias? Does multicollinearity lead to a bias in my estimation? No. Multicollinearity never leads to biasness. It just affects the efficiency of the estimation. And we can have some problems that we cannot introduce some variables together, but multicollinearity does not lead to biased coefficients.
But if I take the first model
Yes?
and with a dummy variable sigma t and a constant term, I think it will be impossible to calculate the matrix x1x and x1x minus 1 because there we have two dummy variable sigma t, and the estimator will take alpha, the constant term, as a constant term. 1, 1, 1.
Now I'm not taking alpha as a constant. It's not a constant anymore. So now I have a new alpha I, which is equal to ui plus alpha. So even if this one is constant, the overall one will not be constant. So it will be changing. It will be variable, I mean. And that's the idea of having an intercept for each individual. Okay? So that's for the fixed effect. Let's make it differently. Instead of introducing this individual effect with the intercept, what we did for the fixed effect, here in this case, I will keep it as it is. So the UI will be part of the error term with the new IT. So here I will have a normal intercept, alpha, plus the beta xit, the slope of the independent variable, gamma tit, which is the individual and time dimension, and the sum of the individual dimension and the error term. Okay? So here the idea is that compared to the fixed effects, my intercept and my slope, they change by individual or they are constant? They are constant. So I have the same slope and the same intercept. Because what made me here have different intercepts is that I introduced in the fixed effect the UI with the alpha. But here the intercept is only alpha. So the intercept does not change across individuals. That's one. Does the beta change across individuals? Doesn't change. So intercepts and slopes are constant across individuals. But now, the individual dimension UI is a component of what? Of the error term. So in this case, UI cannot be correlated with xi, and that's an assumption that we have to do. Or TIT, why? Because if the UI, which is the error term, if I have a correlation between my error term or part of my error term and one of the explanatory variables, this means that I'm going to violate which assumption? No. No, if the exogeneity. Because we said that if there is a correlation between the error term and the explanatory variables, so this violates the exogeneity assumption, right? So in this case, if I want to run a random effect model, UI must not be correlated to my explanatory variables. And that's the main difference between the fixed effect and the random effect. Okay? So until now, what are the differences that we had between fixed effects and random effects? So for both, we have same slopes, okay? So if I have here fixed effect and random effect, so here same slope, different intercepts. Here we have same intercepts. UI is part of my intercept. Here UI is part of my error term. Okay. Here what I wanted to say. Yes, here no correlation between X and UI, and I don't have this assumption here. Okay? It's very strong assumption, and this is why we have to double check that we don't have a random effect, and we're going to see this later. Okay? One final important point, and that's also the difference between the two estimations, is that if I have any time invariant characteristic, again, if I introduce, I'm estimating the effect of education on wages, okay? And I want to, in order to control for all the unobservables at the individual level, I decided to introduce a dummy. What's your name? Sausan. I will introduce a dummy variable in my regression that takes the value of 1 if the individual is Sausan and 0 otherwise. So does this dummy variable change over time? No. As long as I have Sausan in my data set, this will not change. Okay? So this means that if I introduce a dummy variable for Sausan, anything that is time invariant related to Sausan will not be introduced in the model or will be automatically dropped from the model. Example, so again, I decided to control for this unobservable heterogeneity to introduce a dummy variable for Sausan. Let's assume that Sausan was living in Khartoum. And this year, so I asked her this question 2 years ago, and then in the new survey, I asked her, where are you living? She told me, in Khartoum. So this means that her location did not change over time. Is it time variant or time invariant? So it will be dropped because it will be captured by her dummy. If I ask her gender, again, it will be dropped because her gender didn't change over time, and so on. So the problem of, just a second, I'll just continue this. So the problem of fixed effects is that all time invariant variables will be dropped from my estimation. And then I will not be able to study their effect on my dependent variable. Another example, if we take I will take a different example, not from the labor market, but from international trade. If we have a model that tries to see the determinants of exports of each firm, okay? And I decided also to introduce a dummy variable for each firm in order to control for its unobservables. If this firm did not change location, or this firm did not change its, sector of activity, anything that does not change over time will be captured by the dummy of the firm, okay? And that sometimes becomes problematic, even at the macro level. If I work with macro data, like trade data, for instance, and I want to run a gravity model where I examine the determinants of exports from a country to the other, distance between two countries don't change. So if I introduce bilateral fixed effects, this bilateral distance will be dropped. If the two countries, sometimes we introduce in the gravity models also, if the two countries, they share common language. So does official language change over time? It doesn't change over time. So it will be captured by the bilateral fixed effects. So if I introduce a bilateral fixed effect, all the variables that change that don't change over time for the two countries will be captured by the bilateral fixed effect, and so on. So sometimes it becomes a constraint because I want to have the gender variable in my estimation. And if I don't have the gender variable in my estimation, I will not be able, for instance, to examine the wage discrimination, gender wage discrimination, because my gender variable vanished when I used a fixed effect estimation. So, and that's the fifth difference between both, is that here I cannot introduce time invariant variables. Here we can introduce time invariant variable. And we're going to see why here later. Okay? So in the fixed effects, I cannot introduce any time invariant variable because they will be captured by the individual effects. But in the random effect, I can do this. So if I run the same regression for the effect of gender on wages using a random effect, the gender variable will not be dropped because I'm not introducing individual effects with different intercepts. It's just part of the error term. Okay? You had a question?
Yeah, I just want to ask about the location. What about if she changes the location?
So in this case, it will not be dropped.
If only 1 year, after 5
No,
years?
I mean, it depends. It depends on the number of rounds I have. If the location, if we assume that the location for all the firms didn't change over time, so in this case, it will it's time invariant, so it will be dropped.
But if it changes only for one time, it will stay.
Yes?
Within and between.
I'll come to this later.
Okay.
Okay? So any question on what I did until now? So in the fixed effects models, the intercept in the regression is allowed to differ among individuals to reflect the unique feature of individual units. And that's very specific to the fixed effects model. So in general, what we do, we introduce a dummy for each individual. And that's why we call it sometimes the least square dummy variable estimation. Because as if I'm going to run a least square estimation, but it's not the ordinary one because I'm just introducing a dummy variable for each individual. And this is why we call it the fixed effects model using dummy variables is known as the least square dummy variables model. And in this case, as if this individual effect will capture all the time invariant individual characteristics. So in this case, I can call the fixed effect the least square dummy variable. And that's the 6th point. What do we call the random effects? So the random effects, as I said, in this case, my individual dimension will be part of the error or a component of the error term, and the unobservable effects in this case will be stochastic, meaning that they will be random, and this is why we call them random effects. They are not fixed for each individual. So the random effects model attempts to deal with this unobserved heterogeneity, but with a different framework. And in the random effects model, we assume that the intercept value of an individual unit is a random drawing from a much larger population with a constant mean. So what does this mean in practice? In this case, my individual intercept will be the difference between the mean of in other words, the constant mean value, okay? And as if we'll see later that given the fact that this will affect my error term that can become heteroscedastic, yes. In this case, how we resolve this problem? when we have a heteroscedasticity in the estimation. What? Sorry, GLS. What's the GLS? The generalized least squares. And what's the basic idea of the GLS? Exactly, we use weights. So given the fact, just to recap the mechanism, so I introduced the individual effect as part of the error component. Okay? This means that I don't have different intercepts for each individual because I have the same intercept and the same slope. Okay? But in this case, my error term can suffer from heteroscedasticity. And in this case, I have to run a generalized least square, which basically uses weights in order to resolve the problem of heteroscedasticity. And this is why the random effects model can be considered as a GLS. So while the fixed effect model is a least square dummy variable, the random effect is a kind of generalized least squares. And those are the main differences between the fixed effects and the random effects. A seventh point that's also differs between the two techniques is that in the fixed effect model, I have to introduce a dummy variable for each individual, right? And what's the implication of this? What does this affect? My degrees of freedom. Because if I have thousands of firms, I have to introduce 999 dummies for the firms. And in this case, I will consume my degrees of freedom. But for the random effect model, it does not consume the degrees of freedom. And this is why it's much more economical than the fixed effect. So here we have very low. Can you see here or I write it here? So here, low degrees of freedom because I introduce a lot of variables. And here we have a high degree of freedom. Okay? So that's in general the difference between both. How can we estimate this? So as I said, the random effect model in general has a composite error where we have two components in the error term. One which is the initial error, which is IT, and the other one which is the individual dimension, which is UI. So both components of the error term are assumed independent of the included variables in order to satisfy the exogeneity condition. Because if we do not comply with the exogeneity condition, this means that we cannot have unbiased estimates of beta and the other intercepts. So given the fact that this model has two parts of the error, we obtain two variance estimates, which are the sigma square u, which is the variance of the first component, and sigma square nu, which is the variance of the second component. Because now my error term includes two components, the individual one and the IT one. So this means that in this case, the error term is constant or not constant? Sorry, the variance of these two components is not constant because it will be changing across individuals. So in this case, I don't have a constant variance, so I don't have a homoscedasticity. So I have to resolve this by using the GLS. And this is why we therefore estimate the model using generalized least squares instead of the OLS. So bearing this in mind with those 7 differences between fixed effects and random effects, I'll just summarize them again because this is very important when we're going to analyze how we choose between the two models. So there are 7 differences between the fixed effects and the random effects. So for the fixed effects, as I said, they have same slope. Random effect, they have also the same slope because all these techniques, they don't run any random coefficient estimation. For the fixed effects, they have different intercepts. For the random effects, they have same intercept. For the fixed effect the UI is part of the intercept, and this is why we have different intercepts. But here the UI is part of the error term, exactly. And so we have two components in the error term. Here we have no assumption on the correlation between X and U, but here we have to assume that Xi and Ui are orthogonal, or there is no correlation between both, okay? Here we cannot introduce time invariant variables because they will be taken into consideration by the individual time invariant dummies. Here we can introduce time invariant variables. They will not be dropped. Here we estimate this using the least square dummy variables. Here we estimate this using the GLS. Here we have a very low degrees of freedom because we consume most of this with the introduction of several individual dummies, but in the random effect model, we don't have to do this, and this is why we have a lot of degrees of freedom. Okay? So this means that by the end of the day, the fixed effect model is an OLS with dummy variables, and the random effect model is a GLS in order to resolve the problem of heteroscedasticity. So in this case, what I will do, I want to choose between. So we have the very first model that I presented, which is the pooled OLS, okay, against the least square dummy variable model, which is the fixed effect model. So I want to compare both in order to see which one I will be using, okay? So to do so, since the fixed effect is simply an OLS with individual dummies added, it can be tested against the pool cross-section model, which is a simple OLS without least square dummies, using a classical F-test with the corresponding degrees of freedom. So in this case, what I will do, as if I'm going to compare, the classical F statistic, where I have the R square of the least square dummy variables model minus the R square of the pooled variable over n minus 1 divided by 1 minus R square of the least square dummy variable divided by its degrees of freedom. So in general, what does the statistic show, or why is it useful? Because if the F statistic in this case, the F statistic in this case will help me choose between the two variables. It will show to what extent using the fixed effect model is better than, or is the correct one compared to the pooled OLS variable. Yes? No, time series it's different, because in time series I don't have any individual dimension. I just have a time variations, but I don't have several individuals.
The null hypothesis here to prove that both are equal, the pooled estimation.
Yes, and if it's significant, so we reject it, so they are not equal. So we have to use the least square dummy variable.
If the F is greater than 10, you reject the null, so basically they're not.
Exactly. Okay. And for the, so that's for fixed effects and OLS. For the other one, which is random effect against the pool cross section, because I mean, until now, I'm contrasting each model, random effects and fixed effects, with the OLS pooled, right? So we've seen the first one. For the second one, in order to contrast this, I have to check for what? The
relation, the xi and y.
Okay, and what else? I mean, to be more specific. What I want to check in the random effect, the most important thing. Sorry? No. Yes, mainly the heteroscedasticity, because that's the main issue, given the fact that I introduced the individual dimension in the error term. So I want to check whether my error term is heteroscedastic or not, okay? So in this case, we use the Broch-Pagan Lagrange multiplier test, which is a chi-square test with 1 degree of freedom, because in this case, I assume that the variance of the individual dimension is 0, because if it's 0, this means that what happens if the variance of this, I remind you that my error term VI plus, sorry, VIT plus UI, all of this was the error term that I have in the random effect model. So if the variance of this is 0, this means that the variance across individuals will not be variable. It will be the same. So if this is equal to 0, if the variance of this is equal to 0, this means that I don't have heteroscedasticity problem. And in this case, the test that will help me check whether my error term is independently and independently identically distributed or not is to check whether the variance of the individual dimension UI is equal to 0 or not. If it's equal to 0, so we will not have an error term that has a different variance across individuals. Okay? And that's basically what we do in this test. Because if there is if the variance sigma square u is not equal to 0, if sigma square u is not equal to 0, what does this mean? So and I cannot use the OLS because it will affect again my efficiency. Because you know that in general heteroscedasticity affects efficiency. Okay? So until now what I did, so just to summarize what we've done until now, we started with the main concept that we have, which is the unobserved heterogeneity. Then we distinguished between the two main models that we have, which are the fixed effects and the random effects, with the main differences between the two models, okay? And then we saw what kind of tests can be used in order to test each methodology against the pooled OLS. What I want to do now is to test which one I have to choose, the random effect or the fixed effect, okay? So in this case, basically, what's the most important difference between both? The assumption. So I have just to check the assumption, which is whether there is a collinearity between explanatory variables and my error term or not. Okay? So in this case, the null hypothesis of the test is that the individual unobserved effect, so the fixed effects and the random effects, are uncorrelated with the included variables. Right? If they are correlated, in this case, I have to use fixed effect. And if they are not correlated, I can use the random effect. So if that hypothesis is rejected, because what's my hypothesis is that they are uncorrelated. So if I reject this, this means that they are correlated. So, and if how is that? If that hypothesis is rejected, oh yeah, sure, that's correct. Yeah, sure. Yeah, it's correct. So if I mean, it's always very difficult to locate which is the null hypothesis and alternative hypothesis. But here, so the null hypothesis is that my individual characteristics are uncorrelated with explanatory variables, okay? With the included variables xi, which are the explanatory variables. So if I reject this hypothesis, this means that they are, if I reject this, this means that they are correlated. And if they are correlated, can I use the random effect? No, because the random effect model assumes that there is no correlation between the x and the u. Okay? So again, my null hypothesis here is that my explanatory variables are uncorrelated with the individual characteristics. If I reject this, this means that they are correlated. And if they are correlated, I cannot rely on a methodology that assumes that they are not correlated. So in this case, I will have to use fixed effects, okay? If the null hypothesis is not rejected, so both models are consistent. So it's not a matter of consistency. But which model is more efficient? So if I do not reject this hypothesis, this means that my error term, my individual dimension is not correlated to the explanatory variables because I did not reject the H node. If I do not reject the H node, this means that I can use which technique? Random effect. But if I compare the random effect with the fixed effect, which one is more efficient? Random effect, because the random effect controls for the heteroscedasticity, since it uses a GLS. So this means that I'm comparing two different methods. In one case, I have one that will be consistent and the other one will not be consistent. But for the other, both of them are consistent, but one of them is more efficient than the other. What does this mean? In my first case here, so my H node is that my explanatory variables and UI, so their covariance is equal to what? To 0, right? You agree? All of you agree? Yes or no? Then the H1, that the covariance between X and UI. So if I reject H node, this means that the covariance between X and UI is different from 0. So can I use the random effect? Yes? Can I use the random effect? So I cannot use the random effect. So I have to use the fixed effect. Right? If I have to use the fixed effects, this means that the fixed effect is consistent while the random effect is not. Okay? If I do not reject H node, this means that the covariance of X and UI is equal to 0. And then I can use which method? So both are consistent. Random effect is consistent. Fixed effect is consistent. But random effect is more efficient. So I have to use here the random effect, and here I have to use the fixed effect. And that's the basic idea of the Hausman test that compares the two methods. So the test compares the coefficient estimates from both models, and if they are jointly not significantly different from each other, there is no detectable bias in random effect. So this means that the null hypothesis is not rejected and random effect is preferred. Okay? So and this is why we're going to see later in Stata that I test the joint significance of the coefficients of all the variables in my model. Okay? Any question? Okay. So fixed or random effects, as I said, random effects in general are efficient. As I said, because we're using GLS. But why should we assume one set of unobservable fixed and the other random? Sample information more common than that formed from the entire population, in the sense that it's very similar to the population itself. And the most important argument for the use of random effects is that we can include time invariant variables, which is not possible for the fixed effect estimation. Because I remind you that in the fixed effect estimation, all time invariant variables will be automatically dropped. But the problem, the most important argument against the use of random effects is the strong assumption that there is no collinearity between individual effects and the explanatory variables, which is basically the most important thing that led us to use one of these methodologies. Because if you remember, once we relax the assumption of exogeneity, we cannot rely on OLS. Okay? What happens if you remember when I presented that we have 4 cases? I have the same intercept and the same slope, and that's the normal OLS if all the conditions are satisfied. I have same slope, different intercepts. That's the fixed effect. I have different slopes, different intercepts, and in this case, I will have to run a regression for each individual because they are very different. Or I have different coefficients, same slope. Or sorry, different slopes and same intercept. So we have one of the methodologies called, we're not going to see this in detail, but I'll just give you its idea because I don't have time to do it empirically in Stata. So for the random coefficients model, we allowed for either the intercept to differ in the fixed effect or the variance of the disturbance to differ in the random effect across individuals. But what happens if you want to assume that even the slopes will be changing by individual? So this means that instead of having a coefficient, so y, which is equal to alpha plus beta xi, I will have a beta I. So in this case, we're going to have a coefficient that will be changing across individuals. So this would require a relatively large number of time periods because I cannot estimate a coefficient for each individual if I don't have enough observation per individual. So this means that I have enough years per individual. If we did this, the model would look like YIT, it doesn't change, equal alpha, so I have the same intercept. UI, it depends, I will include UI with the alpha and it will be a fixed effect, or with the new IT and it will be a random effect, plus XIT beta I. So the main difference between the random coefficients model and all the models that we've seen is that here we assume that the coefficient itself will be changing across individuals. So one of the methods that can be used here is what we call the hierarchical linear model. If we have enough time span in my data set, so at least 30 years, because for the sake of reliability. And in general, we can use a Chow test that tests to what extent the coefficients across individuals are the same or not. Okay? And that's basically this Chow test applied on the coefficients. We call it the probability test. But here I'm not talking about the structure. Yes, I mean, it's more or less the same idea. But here, the test you're talking about is for time series, whether I have a structural break or not. But here, it's more or less a similar test, but I apply this test on the coefficients in order to see the coefficients at the individual level are the same or are not. Okay? A final, 2 final points on this. The most important problem of panel, especially for surveys, is what we call the attrition. What does attrition mean? Is that I have people who come, people who leave, and I will not be able to really follow the same individuals across time. And if I'm not able to follow them across time, so this means that all what we're talking about is irrelevant. That's one. And the problem also, it's not only at the individual level where I have when I have, surveys, individuals or firms who are that I cannot follow over time, but even for countries, if I'm using a macroeconomic data set, sometimes I have countries that did not exist before and that exist now. For instance, South Sudan, for instance, we cannot have a panel for South Sudan before 2017, right? and for Russia, for instance, before 1991, and so on. So this means that it's sometimes, even at the macro level, it can be difficult to follow the same countries over years. So I will have to do this for a time span where I can follow all the countries across all the years. Okay? So that's the problem, but in general, it's much more pronounced at the micro level, so for households, individuals, or firms, than at the macro level, because, I mean, the dynamics at the macro level are much lower than the micro level. Okay? To summarize all this, how can we choose? And that's the summary of our choices. So can the observation be described as being a random sample from a given population? If yes, I mean, we have to do something, and if no, we have to do something. If it's not a random sample from a given population, then we have to use a fixed effect. And this is why in most of the times when we run macro regressions with countries, in general, the Hausman test tells us that the fixed effect technique is much more, it's much better than the random effect technique, because countries are not random in general. I mean, especially if I'm running, I don't know, a regression including the 145 countries that I have in the World Bank Development Indicators, for instance. So this means that I will anyway have to use the random effect estimation. If it's a random sample from a given population, then I have to perform both fixed effect and random effect. And then what I have to test? I have to test a Durbin-Watson-Hausman test. So if the coefficients are different, if there is a significant difference in my coefficients, so this means what? This means that one of the techniques is biased and the other is not biased. So I have to use the fixed effect. If there is no systematic difference between the coefficients, so I have to use the more efficient estimation, which is random effect. And that's the way we proceed when we have a panel data set. Somebody had a question?
Yes, I was wondering about DWS.
Durbin-Watson-Hausman. Yes. Yes? No, his question.
Just, I have two points. First of all, I would
In the mic, please.
First, I would like just to know if it's required to test the stationarity of fireball in panel data. And second questions, if it is important to use the SEO test of specifications before in panel data, as you know that if we are trying to build an economic relationship, so we need a test to show that it's a panel data analysis. So it's necessary to run this SEO test before go to the next step and fixed effect, random effect.
So for the second question, yes. For the first question, in general, we don't given the fact that the individual dimension is greater than the time dimension. So in general, we don't, in most of the cases, for short time periods, we do not need to run stationarity, because we cannot observe a change in the pattern of the stationarity or non-stationarity unless we have a really long time series. But if I'm talking about 10 years and 140 countries, I mean, in general, we'll not have non-stationary data sets. So in general, we run this when it's the inverse, when we have a time dimension greater than the individual dimension, which is basically the techniques of panel var, panel vec, and so on.
We time series, the behavior of variable change normally when t is more than n.
Yes, exactly. But that's so in general, this is why we have in this case to run tests of stationarity.
Yeah. But if n is more than t, so
no need.
it's not. We don't.
Yes.
Okay.
Because here, the individual heterogeneity is much more important than the time heterogeneity. If I have 3,000 individuals that I'm following over 2 years, so I cannot really test for the stationarity of wages between 2006 and 2012, right?
So for the attrition issue, if we have something of 5-10% of attrition, so what is the impact if we keep only the balanced panel?
It depends on the number of observations that we have. I mean, if the number of observations,
For example, the Egyptian labor force survey, or so we talk about thousands.
yeah.
So
I mean, there are several things that can be done, but in general, if the remainder of the sample that we have is representative enough to run the regression, and that the attrition is not related really to some sort of selected subsample, then in this case, there is no problem, because I have enough observation, and those who disappeared are not, for instance, they are not all of them women, or they are not all of them illiterate, or they are not all of them in rural areas, because this will bias my estimations, or I will have like a sample selection. So in general, it depends on what's the final number of observation that I have, okay, that I can follow across years. That's one. And two, those who suffer from attrition, is it random or it concerns really a specific category of the population?
so we conduct the test as like Ekman, two steps, to see if it's random or not.
Possibly, yes. Yes?
I read in the Vickers book of Waldrich, if we would like to run around the fixed effect, we have to have enough variation. Could you explain?
Enough variation at the individual level. Because in this case, the individual variation, practically speaking, what's the main argument behind using the fixed effect? Is that I have a lot of individuals, and I want to control for all the unobservables at the individual level. So individuals must be very different among them, and if they are very different, so for instance, I have the economy of the United States and the economy of Santa Lucia, for instance. One of is very small and the other is huge, okay? So in this case, there is really a huge variability in my data set at the individual level.
Do we need across unit of observation variation or over time variation?
More individual variation than time variation. Because I have, for all these techniques, I have a much more important unobserved heterogeneity at the individual level than at the time level. Okay?
But in panel setting, it's not necessarily that we need the time dimension. It can be 3 dimensions. That's
Yes.
not like it can be household.
As long as
individual.
it's greater than 1, it's fine.
It's fine. So
Yes.
it's not basically time. We always talk about time,
But actually, to be more accurate, when I'm talking about microeconomic data or individual data, it's not very serious. For instance, if I have household survey, labor force survey, firm survey in 2 rounds, I can use a panel in this case. But I cannot really consider that at the country level,
of course, no.
for just 2 years, that it's a panel.
No, but
So
I
it
mean-
really depends. But as long as it's greater than 1,
Yeah.
it's a panel.
No. I mean, I've seen papers that basically they don't have a time dimension. They have, for example, they have a governorate dimension, then household, then child. They don't have a time dimension. So in panel, it's about having more than one dimension.
So it's, excuse me, so it's assimilated up to panel data because the dimension of, it's like hierarchical structure, so each level it's considered like
Yeah, and then they
timestamp.
perform like within or between.
Yes, but that's another story. Here, you're confusing the argument of within, between
Yeah.
with the techniques of panel.
Yeah.
Panel means that you can use these techniques even if you don't have a time dimension, but you will not call them panel data sets. Because whenever the time dimension disappears from your data set, there is no panel.
Okay.
Okay? But I can, for instance, in the example you said, I can, for instance, calculate the within variation for households and the between variation for between households in the same governor, for instance.
Exactly.
But it's not a panel because I'm not following the same household over time.
Understandable, yeah.
Okay? So it's
But I mean, the
one way,
setting-
not the other way around.
Yeah, but the setting of a panel can be used,
But
not,
not the
panel.
not the setting, perhaps the techniques.
The techniques.
Yes, but the
technique.
setting itself,
You
no, it's
need to
different
have-
because in the panel setting, we're going to see that we're following the same individuals over time.
Yes.
So, for instance, I have, and that's what was Rasha talking about this morning. So I have my identification here. So I have Rami in 98, Rami in 2006, Dalia in 98, and Dalia in 2006. In this case, for me, it's a panel,
Okay.
right? Which is and here I have, for instance, wages. So I have here, let's say, 80, 100, then 100 and 120. Okay? So here, is this long or wide? Long. Because the wide version of this will be ID, Rami and Dalia. They will not be repeated over time. We're going to have wage 98 and wage 2006. So here it will be, 80 and 100, and here it will be 100 and 120.
Okay.
So Stata, in order to understand that we want to run a panel, we must declare two things. We must declare the individual dimension and the time dimension. If I don't declare a time dimension, I cannot apply a panel technique.
Okay.
Okay? Any other question? Yes?
If I have selection bias problem, how can random effect solve this problem?
In what sense?
The food groups I'm comparing are not randomly selected.
So in this case, I mean, either we can use a Hackman selection procedure or a GMM as well, because in this case, but here you're talking about that they are not randomly selected, right? So to my knowledge, the Hackman selection procedure can work.
I think GMM method.
Sorry?
I think GMM method of Arlen and Bond is.
But the Arellano and Bond is another thing because it's for the dynamic panel. And in this case, the basic idea of Arellano Bond is that I instrument the endogenous variable with its slagged values. That's the basic idea of Arellano Bond. So this is why, for instance, if I'm running, I don't know, a growth equation where I have my dependent variable, economic growth. So if I run a dynamic panel, I will introduce the lagged economic growth to instrument the endogeneity of the variable. But that's, in this case, we really need a longer time series. So in general, the Arellano Bond or the dynamic panel in general, if we don't have enough years, will not be able to run it because you lose one round as long as you introduce the lags. So for instance, if I have 30 years and I run an Arellano Bond, this means that I will have only 29 years multiplied by the number of individuals I have. Yes?
I have a question related to the last session. If I would like to do difference in difference using Sheikha as an ID instead of time, we use, for instance, governorate. In using a difference in difference, is it required to set up to define that this is atomic matter in Stata?
But why would you like to use the difference in difference in this case? Why not the PSM, for instance? Because in this case, you'll be able to match, for instance, the shiakha that benefited from a program with, yes?
Is it possible without time?
No, I don't know. You have to check. I mean, to my knowledge, in general, the idea of difference in difference is that we have this before and after. So if I don't have the before and after, I think, but we have to. I mean, we have to check. Better to use the PSM, because in this case I will be able to create the scores for shiakhas that benefited or shiakha that didn't benefit and compare both.
But if you have a panel, why would you do a difference?
Yeah, no. His question is if I don't have a panel.
Okay.
Other questions? Okay, so now we'll break for 15 minutes, just 15 minutes, okay? And then we're going to have a session on Stata. So we will use, I think Ramaj shared with you the folder. So you have the do file, the data set, the do file that you all downloaded the folder, all of you down, the whole folder that Ramaj shared with you through the Dropbox. So we will download Egypt panel data, probably the name of the data set. And the do file is called also panel August 2019. So those are the two files that we're going to use in the last session. So we break from 3 to 3:15 and we start with the empirical part.